Howdy and welcome back. So clause 1 and memory leaks. So if you recall clause 1 to this implicit contract that you enter with the FreeStore manager upon requesting a dynamically allocated object is going to be that you will eventually return the memory for that object that you borrowed when you're finished with the object. The result of violating this clause would be a memory leak. A memory leak is going to occur when we dynamically allocate memory for an object, but fail to ever deallocate that space when we're done using it. Now to go ahead and show kind of a brief example of this, or a simplified example of this, would be imagine the following. We're somewhere in our program and we go ahead and request from the FreeStore manager a dynamically allocated integer object that's initialized with 7. Let's say we go ahead and store the address to that object in P, and we go ahead and do something with the FreeStore object. Before we have an opportunity to return that object to the FreeStore manager, let's assume that we assign P a new address. In this case, P would take on the address of this new dynamically allocated integer object initialized with the value of 11. Now notice here is where the problem arises. If P was our only pointer to that dynamically allocated object housing 7, upon assignment of P to another address, we have just lost any ability to reference this object. Now, why is that problematic? Well, if we do not have its address stored anywhere, we can never call delete on its address. And therefore, this is said to be a memory leak, and that we will never be able to return this object when we're through with it because we have no reference to it. So provide maybe, an additional example, and you've kind of seen this when we introduced the two-dimensional arrays on the FreeStore, is that let's say we have a P is a pointer to an integer object, and let's go ahead and set it up such that P points to an integer pointer on the FreeStore, which in turn points to another dynamically allocated object of type integer initialized with 7. Let's say that, so this essentially sets up this structure here. So this is P is pointing to an integer object, which in turn, P is pointing to a pointer to an integer object, which is then in turn pointing to that integer object. So to kind of, I guess here, just for clarification, let's say that that's this, ooh, that's kind of the same color. Let's do something a little different. That's this object. And finally, P, which is, if you look here, it's a named object, so it resides on the stack. It's right here. Okay, so we can kind of see the different components of this and how it's all fitting together. Now, there's a reason why when we introduced the two-dimensional dynamically allocated arrays that we first deleted, if you remember, each of the individual rows. So remember we had this thing and we array of pointers, and they pointed to arrays out there on the FreeStore. And we said both of these were on the FreeStore. So think about this. If we deleted this object first, we would have lost the ability to access these objects, each of the rows for that two-dimensional array. So ordering does matter. If we wanted to deallocate memory for our two-dimensional arrays, remember first we actually deallocated, oops, didn't mean to erase that. We actually deallocated for each of the individual rows before deallocating memory for that array of pointers to the rows. This is all that example, this example on the slide here is showing, in that we might have some entrance where we set this up and it's kind of the same. We have something on the stack which would have pointed into our two-dimensional array, and then we have these dynamically, so that would be this light blue, and then the rows are kind of in red. If we were to call delete on R, or in this case P first, notice that memory would be deallocated for that intermediary object, which would mean we would have lost any sort of connection to this dynamically allocated integer object storing the value of 7. So why is this problematic here? Because we have no way now to access this object and deallocate its memory. Just like had we deallocated this array of pointers first, we would have had no way to actually deallocate the memory associated with each individual row. So what is the correct way to go about this? The correct way is going to be to deallocate memory by first deleting these intermediaries. So with the two-dimensional array, it was deleting the rows. In this case, it would be deleting the object pointed to by P. So actually calling delete on the address stored within here, which would cause memory for that object to be deleted. Thereafter, we can go ahead and invoke delete on the address stored in P, which would cause this intermediary object to have its memory deallocated for. So that was clause 1 and how violations thereof can result in memory leaks. And again, the whole idea with this memory leak is simply the most common occurrence is we lose our reference to that dynamically allocated object, and then we have no way to actually return it when we're done. And we saw that with the example on this slide and the example on the previous slide. And you might think, okay, well, I'm not going to do something like this. Well, you got to think on a larger scale. What if, this is happening across many functions or whatever? The accounting becomes increasingly more complex. So with that said, let's go ahead and move on to clause 2 and dangling pointers.